Chapter 2 was concerned primarily with the various types of atomic bindings, which are determined by the electron structures of the individual atoms. In this chapter, the discussion is devoted to the next level of the structure of materials, especially to some of the arrangements that may be assumed by atoms in the solid state. Within this framework, concepts of crystallinity and non-crystallinity are introduced. After studying this chapter, you should be able to answer the following questions. What is the difference in atomic arrangement between crystalline and non-crystalline solids? What are the crystal structures of metals? What are the characteristics of crystal structures? How are crystallographic points, directions, and planes specified? What characteristics of a material's atomic structure determine its density? Let's get some background about atomic or ionic arrangements. In different states of matter, we can find 4 types of atomic or ionic arrangements. There's no order, short-range order, long-range order, and liquid crystals. In solid materials, which is the matter we're going to deal with in this course, atoms and ions may be arranged with either a short-range or long-range order. No order means the atoms or ions in the material has no orderly arrangements. The atoms randomly filled up whatever space is available. Think about air or gas, any type of gas. It doesn't have any order. Short-range order refers to the regular and predictable arrangement of the atoms only over a short distance, usually only 1 or 2 atom spacings. So if a material displays short-range order, if the spatial arrangement of the atom extends only to the atom's nearest neighbor or the second nearest neighbors. For example, water vapor. In water vapor, each water molecule has a short-range order due to the covalent bonds between the 2 hydrogen and oxygen atoms. That is, each oxygen atom is joined to 2 hydrogen atoms, forming an angle of 104.5 degrees between the bonds. However, beyond this scale, the water molecules in steam have no special arrangement with respect to each other's position. So this is a short-range order. A similar situation exists in materials known as inorganic glasses, or silica. The tetrahedral structure in silica satisfies the requirement that 4 oxygen ions are bounded to each silicon ion. However, beyond that unit, there is no predictable or periodicity in their arrangement. So many polymers also display short-range order similar to this. The long-range order is a regular repetitive arrangement of atoms in a solid, which extends over a very large distance, even over the entire material. Most metals and alloys, semiconductors, ceramics, and some polymers have this long-range order. Materials with long-range order are called crystalline materials. And based on the number of crystals or based on the orientation, there are 2 types of crystalline materials: single crystal material and polycrystalline material. Single crystal material means a crystalline material consists of only one large crystal, and it is useful in many electronic and optical applications. So in the phone you're using now and in your computer, the chips, a lot of chips are made from silicon, in form of large single crystals. So it's actually cut out from this big ingot, and it's a big ingot, although it's a big ingot, but it's just one single crystal. The properties of single crystal material depend on the chemical composition and specific directions within the crystal, which is known as the crystallographic direction, which we're going to learn later. Polycrystalline material means a crystalline material consists of many small crystals with varying orientations in space. And these small crystals are known as grains, and we are going to learn that as well in the later chapters. And the borders between the tiny crystals are known as the grain boundaries. So this is a micrograph of a polycrystalline stainless steel showing the grains and grain boundaries. So you can see different grains have different colors, kind of, because of the orientation are different under the microscope. And many crystalline materials we deal with in engineering applications are polycrystallines. For example, steels used in construction, aluminum alloys used in aircrafts, so far so on. And we will learn in later chapters that many properties of polycrystalline materials depend upon the physical and chemical properties of grains and grain boundaries. So this long-range order in crystalline material can be detected and measured using techniques such as X-ray diffraction or electron diffraction, which we will also learn in a little bit. How do we describe the crystalline structure? Well, we use this so-called hard sphere model to describe it. In this model, the atoms or ions are thought of being solid spheres having well-defined diameters. So figure A, or all of these figures representing a face-centered cubic, and A is this hard sphere model. So in this model, the spheres representing nearest the neighbor atoms touch one another. So sometimes it's not so easy to draw these spheres touching each other way. Instead, we do this reduced hard sphere model. So we're just representing the location of each atom and with those smaller circles representing each atoms. And C is an aggregate of many atoms. The atomic order in crystalline solids indicates that the small groups of atoms form a repetitive pattern. Thus, in describing crystal structures, it is often convenient to subdivide the structure into small repeat entities like this. We just choose one unit from the entire structure, and this is called a unicell. So unicell is the smallest component of the crystal that reproduces the whole crystal when stacked together with purely translational repetition. So the unicell is the basic structural unit or building block of the crystal structure and defines the crystal structure by virtue of its geometry and the atom positions within. And another term we need to know is the lattice, which is the three-dimensional array of points coinciding with atom positions, or the center of the hard spheres. So we use this concept of lattice to describe arrangements of atoms or ions, and then a group of one or more atoms located in a particular way with respect to each other and associated with each lattice point is known as the basis. For example, in the figure we're seeing here, each pink point can be a lattice point. So we have this kind of cubic system, and we can place atoms on each corner of this cube, and this is the lattice point. So sometimes not only one atom is associated with each location, it can be two atoms, which we will learn later. And this group of one or more atoms is known as the bases. So we obtain crystal structure by adding the lattice and bases. So just like that. We have this lattice structure laid out, and we can finish or describe the entire crystal structure by adding atoms. Locate the atoms on the lattice point. And the atoms we put on each lattice point is called the bases. It can be one or can be more. The unit cell geometry is completely defined in terms of the 6 lattice parameters, which are the 3 edge lengths A, B, and C, and the 3 angles, alpha, beta, and gamma. Well, because of that, we have a lot of different lattice systems, but in this course, we'll just focus on cubic unit cells, which means all the 3 lengths are the same. It's a cube. We use A or A0 to representing the lattice parameter, and all the angles are 90 degrees. Most elemental metals crystallize upon solidification into 3 densely packed crystal structures, and our focus will be on these 3 crystal structures. The first structure is called body-centered cubic, or BCC structure. The second one is face-centered cubic, or FCC structure. And the third one is called hexagonal closed-packed structure, or HCP structure. So we're going to take a look at each structure in more details. Before we check the BCC, FCC, and HCP structure, let's take a look at the most simplest structure, which is the simple cubic. And now you can see this reduced hard sphere model and the hard sphere model of this simple cubic. It has 1 atom on each corner of the unit cell, which is a cube. There's no atoms inside the cubic or on the face or on the edges of this cubic. So if we use A0 as the lattice parameter, which again, just a quick review, A0 is the side of the cube. So all the side has the same dimension, which is A0. So this is the lattice parameter, the length of one edge of the unit cell. Usually, we need to find the relation between the radius of the atom and the lattice parameter. So if the radius of the atom is r, now we can see the atoms will be in touch along the edge. In touch along the edge, like this. So if you just bring the front surface to do the calculation, and now you can see the front surface of this cube, and the length here is A0, which is the lattice parameter, and it equals to, since the lattice point or the corner, or the corner of this cube located at the center of the atom, so this is r, the radius of the atom, and then this is another r. So the relation between the radius of an atom and the lattice parameter for simple cube is A0 equals to 2 times r. Now we are seeing a BCC crystal structure, body-centered cubic. So if you take a look at its BCC structure, it has 1 atom at each corner, and there is 1 more in the center of the cell. So this is the BCC. And we're seeing this reduced hard sphere model. We can change it to this hard sphere model. And from this model, if you take a look at the faces, so now we are seeing one face, the front face. We can see the atoms are not touching along the side, along the edge, right? So there is a gap. There's a gap between the two atoms, so they're not touching each other along the edges. But if you change the orientation and look down, kind of like along the body diagonal, so with two diagonal corners and then with this atom in the center, those three atoms are in touch. Are actually along each body diagonal, the atoms are in touch. So that's the characteristic of the body-centered cube. Now let's figure out the relation between the lattice parameter A0 and the atomic radius r. So we already mentioned that the atoms along the body diagonal are in touch. So now if we just bring the body diagonal out and remove all the other atoms, so we can see clearly, here's one atom at this corner and another atom at a diagonal corner, and there is the middle one is the atom at the center of the cell. So those three atoms are in touch with one another. Therefore, we can find the relation of A0 and R by using this body diagonal of the cube. So the body diagonal of the cube equals to, so if you take a look, the length here is A0, and the face diagonal is square root of 2 times A0. So the body diagonal of a cubic is square root of 3 A0. And it's also equals to, since the three atoms are in touch along this body diagonal, so we have 1r plus 2r plus another r, so a total of 4 times r. So from here we can find the relation between the lattice parameter and the radius of the atoms, or atomic radius, for body-centered cubic. In summary, BCC structure have one atom in each corner and one atom in the center of the cell. And relation between the lattice parameter A0 and the atomic radius is A0 equals to 4r over square root of 3. So the main point here is we need to know that along the body diagonal, the three atoms are in touch, and then we get the relation between the lattice parameter A0 and the atomic radius r. Metals that have BCC structures, including alpha iron, vanadium, chromium, molybdenum, and tungsten. And here you're seeing a face-centered cubic FCC structure with atoms located at each of the corners and the centers of all the cube faces. So this is the reduced hard sphere model. We can rotate it and take a look. And let's change it to the 4 hard sphere model. And if we take a look at the face, or one of the faces, let's take the front face as one example. You can see all the atoms are in touch along the face diagonal. So on this face, we have a total of 5 atoms, 4 at the corners and 1 on the face center. And for all of the 5 atoms, each 3 along the face diagonals are in touch. Now let's figure out the relation between the lattice parameter A0 and the atomic radius for FCC structure. We just mentioned that the closed packed direction, which means the direction along which the atoms are in touch, is the face diagonal. So if we choose one face from the cube from the cubic. Let's choose this front face as the cubic and bring it out. So the side of this cube is A0, and we know the radius of the atom is R. So let's just bring this front surface out so we can have a better view, more clear view. And now we can see the face diagonal. If each side of this cubic is A0, the face diagonal is square root of 2 times A0, which equals to, because of the 3 atoms along the face diagonal are in touch, is a total of 4 times R, similar to this body diagonal in BCC structure, but this is a face diagonal, so it's square root of 2 times A0 equals to 4R. So this is the relation between the lattice parameter A0 and the atomic radius for FCC crystal structure. In summary, the face-centered cubic FCC cells have 1 atom at each of the 8 corners. So you can see the corner atoms are those red atoms, and 1 at each center of the 6 faces. So the blue atoms are the face-centered atoms. So there are 2 different types of atoms locations, corners and face centers. And the relation between the lattice parameter and the atomic radius R is A0 equals to 4R over square root of 2. The metals with FCC structure including gamma iron, aluminum, nickel, copper, silver, and gold. In addition to FCC and BCC structure, the HCP, which is hexagonal closed packed structure, is also a very common crystal structure in metals. This structure is more complex when compared to the simple cubic structures. It requires 2 lattice parameters, A0 and C, but we're not gonna focus on those parameters for HCP structure. You just need to know that many metals do have this hexagonal closed packed structure, HCP. This is the HCP structure shown in the reduced Herd sphere model. And for the HCP structure, if we look the top and the bottom surface, we can see is a hexagon. And the atoms are located at each corner of the hexagon, and also there is 1 at the center of the hexagon. In addition to the top and bottom surface, there are 3 more atoms located within the shape. Let's see the Herd sphere model. It's very close packed. All the atoms are in touch. So we have 3 layers: bottom layer, middle layer, and the top layer. And for each layer, all atoms are in touch. And between the layers, the atoms are in touch as well. Now, in order to calculate the density of the material with a given crystal structure and atomic weight only, then we need to know the number of atoms within each unit cell. Well, to count that, if the atom is located at a different location or different position, it will be shared by different number of cells. So let's take a look at those atoms at different locations. First, for the atoms at the corner. So if you have a corner atom, it will be shared by 8 unit cells. So in this given figure, you can see there are 8 cells stacking together. There are 4 at the front and 4 at the back, and they share the same cell at the corner. Therefore, each corner cell is counted as 1/8. So only 1/8 of the corner cell or corner atom belongs to 1 unit cell. And for the face center, well, let's take a look at, we don't have a face center atom on this given figures, I'm going to draw one. So if this is atom on the face, so it's shared by two adjacent faces. Therefore, each face center atom just have one half. Half of the center atom belongs to one unit cell, so it's half, counted as half. The next one is the body center. So on the right side diagram or figure, we have this purple atoms, which is at the body center. So it only belongs to that unit cell. It's not shared by any other unit cells. So the body center counts as one atom. And if we have edge center, which means if we have one atom, for example, over here on the edge center or at the edge center is actually shared by 4 unit cells, 2 on the top and 2 on the bottom. So each edge center atom is counted as a quarter within a single unit cell. Let's count the number of atoms per unit cell for different crystal structures. First, let's take a look at the simple cubic SC structure. And for the SC structure, there's only one type of atoms, which are the corner atoms. So there are 8 corner atoms, and each corner atom has 1/8, or it's counted as 1/8. Therefore, there's only one atom per unit cell. For the body center cubic, there is one additional atom when compared to the simple cube. So we have 8 corner atoms and 1 body center atom. So 8 times 1/8 plus 1 times 1. Body center, the atom at the body center is counted as 1. Next is the face-centered cubic, FCC structure. So we have 2 types of atoms, corner atoms and atoms at the center. So we know corner atoms, each one is counted once at 1/8, and the face-centered atom, each one is counted once as a half. So only half of the face-centered atom belongs to this unit cell. So it's 8 times 1/8 and 6 surfaces times 1/2. So the number is 4. So there are a total of 4 atoms per unit cell for the FCC structure. Characteristic of the crystal structure is the coordination number, which is the number of atoms touching a particular atom or the number of nearest neighbors for that particular atom. Take simple cubic as example. If you're looking for the coordination numbers, we can pick any arbitrary atom, like this grey atom, and then count how many atoms are in touch with this atom. So again, we're going to choose those neighboring unit cells, and we find there are a total number of 6 atoms are in touch with this gray atom, and they are the nearest neighbors to this gray atom. So the coordination number for a simple cubic is 6. With the same idea, we can find the coordination number of BCC structure. So for BCC, the easiest way to find coordination number is to use this body center atom, and we can see the close or the number of nearest neighbors are those corner atoms. So there are 8 corner atoms, therefore the coordination number is 8. And next is the FCC structure, which is a little bit more complicated. But if you choose this corner atom and then count the number of nearest neighbors. The nearest atoms to these corner atoms are the face atoms, which are the yellow bars here showing in this figure. So to be more specific, those are the yellow bars located at the center of these adjacent faces. So here are 4 faces on the top layer and in the middle and here on the bottom. Okay, so 4 plus 4 plus 4, a total of 12. So the coordination number for FCC structure is 12. Another very important characteristic of a crystal structure is the atomic packing factor, APF, which is the volume of the atoms within the unit cell divided by the volume of the unit cell. So we know because we're going to fit in all the spheres into a cubic, there will be some white spaces or there will be gaps between the spheres. So this APF will tell you how much of the volume within the unit cell is packed with atoms. The rest of it will be the gaps between them. So here's the formula. Volume of the atoms in unit cell divided by the volume of the unit cell. And when calculating this APF, the volume of the atoms in the unit cell is calculated as if each atom was a hard sphere. That means if we have the radius of the atom, then the volume of the atom, each atom equals to 4/3 pi r cubed. And we're going to do some examples in a separate video. We can get the theoretical density for metals using the given unit cell information. So instead of calculating density using the overall mass and volume, we can use the mass of atoms in one unit cell divided by the total volume of the unit cell, which equals to n times A over Avogadro's number divided by V, the volume of the unit cell. So this is the formula that you can use directly to calculate the theoretical density for a given metal, where n is the number of atoms per unit cell. If we know the crystal structure of the unit cell, we know the number of atoms in each unit cell. A is the atomic weight, and V sub C is the volume of the unit cell. And we're going to deal with the cubic systems only. Therefore, if we know the A0, the lattice parameter, we can get the volume of the unit cell with A0 cube. And Na is the constant, which is Avogadro's number. You use this value given here.